Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture number 17 of the course Robot Motion Planning. In the last class we looked at the motion of a car-like mobile robot and the kinematic constraints that such robots are subjected to. For example, they cannot move sideways. Okay. Now today we'll move on with the same discussion on kinematic constraints and then look at controllability. That is, if a robot is subjected to this kinematic constraints, then what happens to the controllability of the robot? Okay, so in the last class we were looking at kinematic constraints, and I'll very briefly go through what we were doing in the last class just to revise, and then we'll move on to controllability. Now we said that a vehicle like a car, okay, which has two control inputs. For example, there is a drive at the back, so drive and steering. Okay. So it has V and phi as inputs, whereas the output is 3 DOF output. That means we have x, y of the center point P, that's my point P having coordinates x and y, plus there is an angle theta. Okay. Now we said that when this car moves, it has a particular velocity v, and the direction of the velocity vector is always in that direction. Okay. And because of which, if the car is taking a turn, for example, if it is turning about this point like this, what is going to happen is that at that point, so let's say the car is turning like this. So at this point, what will happen? The velocity vector will be tangential to the point on that curve. Okay. Now, because of which, because this is my velocity vector v, if I take its projection in the x direction and y direction, what we get is dx by dt is v cos theta and dy by dt is v sin theta. Okay. Now, the local axis of the car is in this direction. Let me draw the local axis also. So the local axis is in this side. That's my local axis. Now, because of these two, dx by dt equal to v cos theta and dy by dt equal to v sin theta, when I divide both of these equations, this by this, what I do get is that dx sin theta minus dy cos theta is equal to 0. Now, this is what is the non-holonomic constraint which this robot is subjected to. And what does it mean? It basically means that when for conditions where theta is equal to 0, the velocity in the y direction will become equal to 0. And when theta is equal to 90, then the velocity in the x direction will become 0. Okay, which essentially means that the car cannot move sideways. Okay. Now, so this is something that we have seen in the last class. Now, something to remember very carefully is that at this point, the velocity vector is tangential to the curve, because of which the car is turning, right? It's taking a curve. Now, if it is turning, then it has the instantaneous center of rotation, which is located at this point, and rho is the length from the instantaneous center of rotation to the center of the front wheel there. Now, if that is the case, and rho also has the turning radius phi would be having a maximum and a minimum. For example, a car can turn only maybe 40 degrees left or right. It can't turn more than that. So, because of which, we end up with a constraint that x dot squared plus y dot squared plus rho minimum squared into theta dot squared must be greater than or equal to 0. Okay. Now, this comes from here, where 1 by rho min is equal to 1 by L tan phi max. And we can get this from geometry. Now, just from geometry, we can get this equation in terms of the L, the length between the center of the front wheels and that of the rear wheel. Now, because of this constraint, what is happening is that the velocity vector that is there. Now, let's look at this again. So, this is my center point P, and this is my PXY. Okay. So, when it is taking a curve like this, on my XY plane, this is my XY plane. On the XY plane, this is the curve, right? It is taking. Now, at that point, what is going to happen is, depending on the theta, this is my theta axis, at that particular location, the velocity vector is going to be tangential to that point there. okay, depending on whatever theta you are on. Now this is one. Now we also saw that the velocity vector is bound by this equation here because of the turning radius by this equation. So what would actually happen is that this velocity vector is also constrained to lie inside a cone. Okay, so this velocity vector first of all has to lie on this plane, okay, for a particular theta, and because of that maximum turning angle constraint that is put, the velocity vector has to lie inside this cone, okay, which is constrained by that equation which is here, x dot squared plus y dot squared minus rho min squared theta dot squared, okay, which means that the vector has to lie inside here. It cannot lie anywhere outside because the turning radius is constrained. Now, that basically tells us that we can think about this as a tangent and a tangent space. So you understand very nicely that this is a tangent, right? So this is a tangent to the curve at this point. Now, at that point, there can be many curves, right? This car can take different turns, so there can be different thetas. So there can be turns in this direction, all passing through that point. But the tangents would be in different directions. Okay. Now, the collection of all those tangents makes up a vector field. Okay, and this is better to or easier to understand like this. If we have a sphere like this, okay, you can imagine that there is a path which is coming from that side, coming like this, and coming this side. Okay, so this is a curve on a sphere. This is on the other side. Now at this point, let's say x naught, we have a tangent which is like this. Okay. Now on this at this point x naught, there can be other curves. So you can very well imagine that there can be other curves here. Now each of those curves are going to have tangents. Now collection of all those tangents are what makes up the tangent space. Tangent space at x naught, at the point x naught. And now there can be different x naughts. The x naughts can be different at different locations on the sphere, which means at each of these x naughts, okay, there can be different curves, and each of them will have a tangent space. So the collection of all these tangent spaces together make up what we call a tangent bundle. Okay, so now we have seen the concept of a tangent space and the concept of a tangent bundle. Now we have also seen that any kinematic constraint can be written in the form GQ Q dot. In the case of a non-holonomic kinematic constraint, basically it is written in this form, and what we have seen that these are functions of velocity, like in this case. Okay, there we have a dx and a dy. These are incremental velocities. Now at any given configuration, the robot velocity can be expressed as a linear combination of different vector fields. Each of this is a vector field, which are a set of independent vector fields spanning a delta. Okay, so this basically tells us that at any given configuration, the robot's velocity can be expressed as a linear combination. That's what we have seen, that they are vector fields, right? And which are a set of independent vector fields spanning all of delta. Now x and y are a set of independent vector fields in delta. Now what is this x and y? This is my x in the x direction, that is my y in the y direction. So there are different vector fields, okay, at any given configuration of the robots, and this velocity can be expressed as a linear combination of x1, x2, x3, x4, which are a set of independent vector fields spanning delta. Okay, now we move on to what is controllable and not controllable. Basically, why this question comes up is essentially because we have seen that there are two control inputs. The control inputs are only wheel velocity and that steering angle phi, but the outputs are x, y, and theta. They are 3. So this is 2 and there is 3. Okay. So, for example, if you look at this picture, this figure here, is it possible for this car to go and park there? Okay. So the car is here. This is my initial point, and this is my final point, or this is my goal configuration. Let's say this is my goal configuration. Is it possible to go and park? Okay. How do you know? Now, if the car is only moving forwards, then it is impossible to get to the final position. Whereas if the car can move forward and can move backward, then the car can go and park like this. So for example, it goes front like this and then it goes back like that, and it has parked in this configuration. Okay. Now in this case, the car is controllable. In the previous case, the car is not controllable. Okay, now I hope you understand the meaning of not controllable. Means you can't get to that desired position. Now this was an easy example, and we have eyes, so we can see and try and figure out that, okay, maybe it can move like this and move like this and go there. but you would remember that in path planning, this program which is doing this automatically. Okay, so how would the program figure out? Is there any mathematics behind that? Now, so controllability is two control inputs for controlling a 3 degree of freedom system. Now, due to a non-holonomic constraint, some motions are not possible. This we have seen. For example, a car cannot move sideways. Okay, so this car cannot go sideways direction, right? That's not possible because of this non-holonomic constraint. So it is natural to ask if the car or mobile robot can reach all positions in the workspace. Can it reach all positions? So I have a workspace like this, and I have a car. So the question being asked is, this car is subjected to a non-holonomic constraint, which means it can't go sideways. But can it go and park anywhere in this workspace? That means, are all configurations possible? Okay, how would you figure that out? Okay, is there some mathematics behind that? That is what we are looking at here now. So I have a mobile robot which is subjected to a non-holonomic constraint, and I want to find out if this non-holonomic mobile robot can go and park at any configuration in this workspace. Okay. So we're trying to answer this question of controllability. So the control Lie algebra associated with delta, denoted by CLA. So CLA stands for control Lie algebra, is the smallest distribution which contains delta and is closed under the Lie bracket operations. So we'll just come to what is Lie bracket. CLA is a distribution generated by x1, x2 and all their Lie brackets successively computed. What this means, I will just come to and explain. Okay. So we are seeing this new term, control Lie algebra associated with delta, denoted by CLA. Delta is the smallest distribution which contains delta and is closed under the Lie bracket operation. CLA is the distribution generated by x1, x2 and all their Lie brackets recursively computed. Okay. Now, any two configurations, Q initial to Q final, of an open connected subset of C is the configuration space, can be connected by a physical path by following the flow of a finite sequence of vectors of delta if and only if the dimension of CLA is M. Okay, that means that the control Lie algebra of delta is M, which is the dimension of the configuration space. Okay, let us try to understand this by looking. I'll just come back to this page again, but let us look at this example. Okay, what I'm trying to explain here, or what this mathematics is all about. So first of all, it says that suppose there is a mobile robot which cannot go sideways. Okay, in that case, by a combination of motions, can it actually go and park sideways? Okay, for example, this is a mobile robot. This is a car kind of a mobile robot. Now we know it cannot go sideways. Okay, but then by making up or following different paths, can it actually successively have different paths and then finally go and park sideways? So in that case, it is not going sideways exactly and parking there, but it is probably making a series of maneuvers and then going there. Say for example, it goes like this, then comes like this, then goes like that. Okay, but it has actually gone sideways, but by following different paths, not exactly there. Now let's take the case of a wheel. Okay, now this is a wheel. Okay, as you can see in this figure, this is a wheel. Now in this wheel can rotate about its axis like that. So this, suppose I say there's an axis there, so it can rotate like this. Okay, and it can twist about this axis. So there's one more axis here about which it can turn. So this wheel can rotate and it can steer. If that is my steering axis, then it can also change its direction there. So this, it can rotate and it can become in some other direction. Okay, so there is a theta there and there is a velocity here. Now let's look at this video and it becomes clearer there. So this this vehicle or wheel can go forward like that. It can roll forward, it can rotate forward, and it can go back like that. Okay, so rotate forward and go back like that. Okay, and it can twist about its main axis. That's the steering. It can steer about the main axis. So this is my steering. It can twist like that, just like a unicycle model. Okay, so it can twist about the axis. So it has two motions. The one motion is it can go front and back. You can see that. The number two is it can twist about its axis. Okay, this is what it can do. Now, the wheel cannot go sideways. Okay, see, the wheel cannot go sideways. This sideways motion is not possible because of that single non-holonomic constraint. Okay, so because of this non-holonomic velocity constraint, this robot cannot go sideways. Okay, so my question here is, we know the robot cannot go sideways. Okay, but it has these two motions. It can rotate and it can. So in that case, how would you make it go and park sideways? So just see what is being done. It is going forward Okay. So this is my first motion. Notice this carefully. It goes forward, it rotates forward, then it twists, and the steering angle changes, then it goes straight back, then the steering angle changes again. Okay, I'll replay it. So here, what it is doing is, it is going forward. That is one velocity vector field. It can have different velocities, so that is a vector field. That is one. Let's call it x1. Next, it can steer. Let's call it x2. Okay, sorry. Once it goes there, it is turning. This one you can see it is turning there. So that is my x2. That's another vector field. Then it's going back in a straight line. Okay. Now because it is at an angle, you can see it has gone at an angle. That is my vector field 3. And it has again steered. That's my vector field 4. Or I can say x1 is the forward direction, x2 is the rotation, x3 is back, and x4 is minus x1, x2 again. Okay. That is what I mean by saying that this, what we are talking about here, that any two configurations, Q initial and Q final of an open connected subset of C is the configuration space, can be connected by a feasible path by following the flow of finite sequence of vectors. Okay. So we have a finite sequence of vectors, which is, it was going forward, it was changing the steering angle, then going back, changing the steering angle again. So those are a finite, it's a flow of finite sequence of vectors of delta, if and only if the dimension of CLA is M, and where M is the maximum dimension of the C space. So this basically tells us that this car, which is subjected to a single non-harmonic velocity constraint, can actually go and park if we can get a sequence of vectors x1, x2, x3 vector fields like this, and using control Lie algebra, if we can generate vector fields such that this can go and park there, and that can only happen if the dimension of the of delta is equal to the dimension of the C space. Okay. Now there's a corollary here. The corollary is any robot that is subjected to a single non-singular scalar non-harmonic equality constraint is fully controllable. That means if you have a single constraint like this, which is given here, that a car is subjected to, such systems are fully controllable. Means you can take and place them anywhere, okay, inside the workspace. Now, let us look at an example which will make it a little bit clearer. But okay, so let's look at an example which will tend to make this clearer. So what this is basically telling is that a single wheel can move sideways by combining different motions. This is x1, x2, x3, x4, like this. These are each of this is a vector field. Okay, so this is a single wheel. Now it can rotate forward, similar to the wheel that I just showed. This can rotate about that axis, and it can steer about that axis. So it has two inputs now. There's a velocity, let's call it omega, and there's a steering angle, which is phi. Okay. Now with these two inputs, can it go to every position in every configuration in the workspace? Now the configuration has 3 dimensions, right? So the vehicle has a normal car has x, y, and theta, right? So now what we can see is, let me take the top view of this wheel. This is my top view. This is the axis. Okay. So if this is the top view, it can rotate forward. It has gone forward like this, what I just showed in the video. So it has gone like this, it has gone forward. Then what we do is we rotate, or we change the steering angle. So if I change the steering angle, it comes like this. Okay. So this was x1, this is x2. It has turned in that direction. Okay. Then x3 is, it comes backward like that. Okay. I can say this is minus x1. Okay. So it has come backward. The car has the wheel is positioned here now. Okay. And then what I do is I do minus x2 again. I do minus x2, so it comes here. So it goes this side, so it becomes minus x2. Okay. So you can see that this was plus x1, that is minus x1. This plus x2, this is minus x2. Okay. So what it did is basically it used different maneuvers to actually go sideways. And it has gone and parked sideways like this. That means this point here in the configuration space is accessible. The robot cannot go sideways, or this wheel cannot go sideways, okay. But then by using different maneuvers, it can actually go in position there. That means the system is fully controllable because it can go and position at every point in the workspace. Okay, now let's go back to the definition again and try to make sense out of it. So it says that the control-Lie algebra associated with delta, denoted by a CLA delta, is the smallest distribution which contains delta and is closed under the Lie bracket operation. I'll just come to what is Lie bracket operations. Okay. Now CLA is the distribution generated by x1, x2 and all their Lie brackets recursively computed. We have seen what is x1, x2. Now any two configurations Q initial to Q final of an open connected subset of C can be connected by a physical path. That means it can go from Q initial to Q final by following the flow of a finite sequence of vectors of delta if and only if the dimension of CLA is M. That means the dimension of the control Lie algebra is equal to the dimension of the C space. Okay, in that case, the system is fully controllable. This is what it is saying. Okay, so here we saw the example that this wheel can actually go sideways just by making different maneuvers. First it goes like this, okay, then it turns that side, then it goes back, okay, and then it turns in that direction. So this is x1, this is x2, this minus x1, and that is minus x2. Okay. Now, so this is the case of a single wheel that can move sideways by combining different motions. Now let's look at the mathematics of control Lie algebra. Now what is control Lie algebra? In this particular case, it was moving forward by x and turning y. So x and y are vector fields. Okay. Now the Lie bracket operation is written this way with bracket x and y. This is some sort of maneuver based on two motions x and y. X during del t by a small amount del t during that time, and y during del t, minus x during del t and minus y during del t. Now what this basically means is that this wheel can go forward. This is my velocity vector, v cos theta and v sin theta, and the turning angle is phi, so it can turn by this much. Okay, now let's look at it here. So this is my starting point. So it went like this, x, then it went turned y, then it went minus x, and then it went minus y. That is exactly what I did here. Okay, so there was a plus x, x1 is plus and x2 is plus, then it went minus x1, then it went by this amount x2, minus x2. So this is exactly what it is doing, and in the process it is going from here to here, which is actually sideways motion. Okay, so by changing this combination, now there can be different x's, right? It can go like this, like this, like this, like this, like this. All x's are possible, whatever x's are possible. So by using different x's, it can go sideways and park in different places. Okay, that means all points here are actually controllable. So the wheel can go sideways and park anywhere. Now let's look at this again. What control Lie algebra is actually doing is by using Lie brackets, we are generating another motion, okay, which is given this way. So this is basically generating a new motion. So it is taking x vector field, y vector field, and then generating another motion by using this, by using Lie brackets. Now what this basically means, suppose you are at q and you want to go to q dashed. There are basically four motions that are required. And it means from here, if you look at the limit del t going to 0, q minus q dash by del t squared. If I take the Taylor series expansion of that, what I get is this term. Okay. So what I do is I use Taylor series expansion on this, and I get dy into x minus dx into y, okay, using Taylor series expansion, where dx is equal to x1 by dx, x1 by dy, x1 by d theta. In our case, remember, for the car, it is x, y, and theta. These are the three variables that are there. Then x2 and x3. So this is my dx. Similarly, dy is that dy1 by dx, dy2 by dy, and dy3 by d theta. Okay, that is my dx and dy. Okay. So what this is telling us is, if you have two vector fields x and y, by doing this operation, which is called Lie bracket, you can generate a third motion. Okay, this is a third possible motion, and successively you can generate different motions simply by taking the Lie bracket of these vector fields. That is what it is telling us. So let's look at the analysis of this unicycle. Now for this unicycle, let's look at it this way. So this is my unicycle, that one wheel, and the kid was sitting on top of it. That is this one. Okay, so this is the unicycle. Okay, so this is one wheel which can rotate about that axis, and it has a steering about the vertical axis. So if you look at that one wheel, then basically this is my wheel. Okay, it is making contact there. So I can say that the unicycle x dot is equal to x1, x2 and x3. These are vectors x1, x2 and x3. So x, y and theta, okay, which I can write in terms of q as q1, q2 and q3. Okay. Now in terms of velocities, I can simply put a dot there indicating that these are, I can also find the velocity. Now in this particular case, let us write down the frame of reference. This is q1, that is q2. This is, so at the contact point it is q1, q2 at that contact point, and this is my, and it is pointing in this direction, so that is my q3. Okay, so x, it is like xy of this point, and theta is the angle, the steering angle. Okay. Now this wheel can roll forward or backward, okay, and it can spin about a point, or we can also call this steering. Okay. Please note that it has to go forward and backward. In the case of the car we saw, if the car can go only forward and not backward, then it's not controllable. So it has to be able to move forward and backward, and it must have a steering. Now suppose I define two vector fields when the robot is going forward and turning. So forward, going forward is equal to, let's call this is one vector field g1, and this is equal to cos x3, sin x3 and 0. Okay, so this is going forward with unit velocity. So this wheel is rotating about this axis with unit velocity. Okay, so in the x direction and y direction, it is going to be cos theta, cos x3 and sin x3, and that is going to be 0 because this contact point is always there. Okay, now what about the spinning or steering? Steering is another vector field g2, which is equal to 0, 0 and 1. Let's say unit velocity. Okay, so we have two vector fields, one vector field for going forward and another vector field for turning, for changing the steering angle. Now I can draw this vector field in terms like this. This is my x1, x2. This is x1, x2, and that's my x3. This corresponds to xy and phi if you want it that way. So if it is going only in the x direction, these are the vectors of the vector field which are pointing in this direction. It is going only in the x direction. Okay. Now if it is going only in the y direction, then I can have another one here which is going only in the y direction. Okay, this is going only in the y direction. And if it is going only in the z direction, then I can also have a set of vector fields which are going only in the y direction, sorry, in the x3 direction. This is my x1, x2 in that direction. Okay, so basically what we are saying is that the final motion of this wheel is going to be made up of all these vector fields, and to perform the Lie bracket, I'm going to take one vector field of going forward, one vector field of steering, and I'm going to perform the Lie operations and see if I can generate another vector field. Okay, so what we do here is basically I'm going to use this formula. Okay, this formula I'm going to use. Okay, this formula I'm going to use here as given here. So the way we write it is G1, G2 with this bracket is equal to differential of G2 by dx, partial differential of G2 by gx into G1 minus derivative of G1 into G2. Okay, this is exactly what we wrote from there. Okay, so this is, if you just go back and see what is written here, is this. Okay, derivative with respect to the second field into x, and derivative of the first field into y. So this is my first field and this is my second field. The way we have written it here is like this. Okay. Now remember what is G1 and G2? G1 and G2 are given here. g1 and g2. Okay, so if I take the derivative now, this is going to become equal to d of g2 by dx1, d of g2 by dx2, and d of g2 by dx3, partial derivative of g2 with x into g1, minus of d of g1 divided by d of x1, d of g1 by d of x2, and d of g1 by del of x3, okay, into g2. Okay, so this is equal to this. Now all I have to do is put in the values. So let's look at, I'm taking the derivative of g2 with respect to x1, x2, x3. What is g2? g2 is 0, 0, 1. Okay, so it doesn't contain x3 at all. Okay, so basically this is going to become equal to 0. So I have 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, and what was my what is g2? g2 is equal to cos x3 sin x3 and 0. Okay, so this is cos x3 sin x3 and 0. Okay, minus what is the partial derivative of g1? This 0, 0, 0, 0, and here we'll be getting minus sine x3 and cos of x3, and this is my 0, and this is equal to 0, 0, 1. Okay. So this term will fully become 0 because this matrix is fully 0. This is fully 0 here. So this term will fully become 0, and what will be left with is equal to sine x3 minus cos x3. So there's a minus sign here, so this minus and minus will make it plus, and this will become minus cos x3 0. Okay. So I have generated a third. This is my g3 now. Okay. So this was one vector field. This was another vector field. I have generated a third vector field now by using the Lie brackets. So this is what I call by Lie brackets. Okay. So I have taken two vector fields, performed the Lie bracket operation, and have generated a third vector field now, which is sin x3 and cos x3. Now let us go back and look at what is the meaning of this. So this was my this is the axis. So let me draw the figure again, or can we do it here itself? So basically what we are doing here is, if I look at the top view is in this direction. I'll just draw it in the other figure. So no space. Okay, I'll just draw it here. So if I draw my axis here, x1, x2, and x3. Okay. Now, how did this wheel go sideways? Basically, if this is my x-axis, x1, and that is my x2, then the wheel was here. Okay, the wheel first moved forward. So this is my wheel, top view. Okay, this is my top view. It moved forward, it went there. Then it rotated. It rotated like this. Okay, then it came backward like this. Okay, and then it rotated again. Rotated means there was a steering angle change. It became like this. That's how it went sideways from here to here. Okay, so this was one vector field x1. This is another vector field x2. This is a minus x1 and it's a minus x2. Okay, so if I draw it in terms of axis, it went in this direction. This is my g1 vector field. It went forward. Okay, then what happened is it rotated. So if it rotates, means it is using the x3 axis. So it is rotated by some angle. The steering has changed. Okay, so this is my g2. Now it has gone back again. It has gone back. This is my g1. This is minus g1. And it has come here. Now this is my minus g2. Okay, because it is having a steering and rotating, it will not come back to x1, x3 plane. This is going to be a slightly different point. So this is my minus g2 now. Now if you look in terms of what was the third vector field that we obtained, what was the vector field that we got? We got sine x3 minus cos x3. This is the third fellow. Okay, this is my g3. This is g3. So sine x3 cos x3. sine x3 cos x3. So it is what we got the third fellow g3 as sine x3 and cos x3 minus. So if you look in the x direction, this is my x is in this direction, right? So it has gone minus in the y direction, which is indicating that it has gone in the minus direction here. So that is my x1, x2 axis. So it has come here now. It has moved sideways. So this is my minus cos x3. Okay. So now this is indicating that wherever we started off from cos x3 and sin x3, and we generated another field which was a sine of x3 and minus cos of x3. Now because this is a minus, it is showing that it has gone sideways actually. Okay. So this basically is telling us that the vehicle has actually gone sideways and it has parked by using a third vector field, which is g3 now. So successively I can have another vector field g1 and g3 now, okay, or g2 and g3 to generate another motion. So by successively generating these motions, the car can go and park anywhere. This is what it is saying. So basically, let's go back to that definition again that we talked about. Okay. So the theorem is very important there. So it says that any two configurations in Q initial to Q final of an open connected subset of C can be connected by feasible path by following the flow of a finite sequence of vectors, okay, using control D algebra. And the system is controllable if and only if the dimension of control D algebra is M, which is the dimension of C space. Okay. So this is what it is saying in terms of controllability. Now, and this also we can use to prove that the single wheel is actually going sideways, because by using Lie brackets we are generating a third vector field which is actually making it go sideways, means it has a velocity in that direction which can actually go sideways and go and park anywhere it wants. Okay. Now this is basically to do with control Lie algebra, and by using Lie brackets we can prove that there is a forward direction of motion which is given here. There is a steering motion here, but Lie brackets is giving you a third motion which is also possible, which is actually sideways. Now the sideways fellows is a combination of other two vector fields. Okay. Now by successively using different Lie brackets, so G1 and G3, G2 and G3, I'm going to generate more vector fields. So each of this will become a new vector field. It may be new, may not be new, but I can generate more vector fields, right? So this is how we use Lie brackets to try and generate other motions, okay, which apparently seem to be constrained by the non-holonomic constraints. Okay. So if the system like a car or a wheel is fully controllable, okay, because again they are subjected to a single non-holonomic constraint, and hence such systems are fully controllable. That's what we are told. That means if this is my workspace and there is a car there, you should be able to take this car and park it anywhere you like, not with one motion but with many motions, okay, following many paths. Let's look at one example here. The car is here. I want to park it sideways. Okay, I want to park it exactly here. Okay, so I want to take this car and I want to park this car sideways. We looked at the example of the single wheel robot. No, this is the case of a car. How is it possible to? It cannot go straight like that. But Lie algebra tells us that there is another vector field which can actually take it sideways. Now, how do we do that? It takes a curve like this. Okay, the car is here now. Okay, so it has taken the steering wheel. It has taken a particular angle phi. The car is here now. Then the car goes backwards. It is here now. Okay, so it has gone straight back like this. Now here it turns its steering wheel that side and then goes like this, and it has parked here now. So the car has actually gone and parked there. So there was one motion here, second motion here, and third motion there. Okay. Now because the car can have different steering angles, of course there is a limit to that. It has different steering angles, so it can have for different steering angles it can have this kind of a circle, okay, or it can have slightly wider circle, okay, or it can have maybe a slightly smaller circle there, depending on phi now, the turning radius. From here it can probably come backward like that and then go again. Okay. So by doing this set of motions, the robot can actually go sideways and park wherever it wants, okay, because the system is fully controllable. And we are able to prove it by showing that if it has a set of vector fields like this, we can use Lie brackets and then generate other vector fields, x1 and x2. We'll give you a third one, x3, which can be in some other direction, can be sideways. Okay. Now this is mathematically showing us that the car can actually go and park sideways using Lie brackets. Now in terms of an algorithm, how do you make the car go and park sideways? That is what is more interesting to us. Now let's look at this example a little bit more detail. What did this car actually do? The car actually changed this angle del theta. So if this is the angle that it is making with the center, depending on whatever is the turning radius, this is my turning radius, that's phi, right? So depending on this turning radius, there is going to be a del phi. So if I look at my graph, if this is x, y, and phi, if this is x, okay, if this is my x-axis, y-axis, x-axis, y-axis, and that's my theta axis, this side, then the first thing it did is it changed the theta angle. Okay, so basically it changed the theta angle. So from here it went up like that. So it is changing this one now. So this is what it is doing. It is going here. Then it went back straight. Okay, so this is my straight motion. Okay, so it went straight and then it changed the theta angle again to come back here. So what it is doing, it is basically having a cylinder kind of motion, which basically means that it is taking a curve like this, which is on the xy plane, okay, with a particular del theta. Then it is going straight, it is on that plane itself, it is going straight there for that particular del theta, okay. And then it is changing the del theta, coming back here, changing the del theta, and then going here, okay. So basically this is a cylinder, okay, or we can call this a cylinder of unit motion. Now by having a connection of these cylinders, we can make it go in different directions. Now let's look at this example again. The car is here. What about pure rotation? I am wanting to rotate the car and face it this side. Okay, in the previous case, in this case it was going sideways. We are talking about the system going sideways. Here we want to rotate the car, so the car is like this. Let me draw and explain it again. This is my car. So this is the point P. I want to rotate the car, and let's say I want to rotate it and make it like this. At that point, okay, can a car rotate like this, about this point? Okay. In one motion it cannot because of that non-harmonic constraint. But what you can do is, see, the car is here initially, the blue one, it goes forward like this. Okay, it has a particular steering angle phi. Once it has reached this point, it is like this now. Okay, then it comes backward. It becomes like this. Okay. Then you turn the steering angle like this. It takes the turn and comes here. So what happens? The car is now here. Okay. So this is actually showing you that there is a pure rotation about that point P, and you can again prove this using Lie algebra by using Lie brackets. That the car can actually rotate. You can take any angle. The car can actually go and position at any angle. Okay. The previous one showed that the car has actually gone sideways. This one is showing you that the car is rotating about that point now. That means it can take any rotation. That means it is fully controllable, so it can take all rotations. Okay. Now, what about a combination of this? Okay. Turning and, say for example, it can, suppose the car has to go and park here. Okay. It can take a combination of these motions like this, 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 and then go there. Each of this one unit was one motion that I showed here. Okay, so this is one unit. So this is my 1 unit. Okay, and by having a number of this, we can actually go and park anywhere. Okay. Now, coverage of a path by cylinders. Each of this path can be covered by small cylinders, each one corresponding to one maneuver. Okay, so here we have small cylinders which are covering, and it is going from one point to another point and achieving. So here, for example of a path, suppose the car has to go and park there. What it is doing is it is taking one set of cylinders like this, then it's making a small set of cylinders like this, and then going and parking there. So although it could not go like this directly, it went there. Now the next important question here is, are there other ways? Now, for example, if it does this kind of a rotation kind of a maneuver, you can rotate about this point, go here, okay? And after going here, you again maneuver and rotate yourself. So what I'm saying is that in the previous case, what we were doing, so in this case, the car wanted to go sideways, it was like this, it had to go there. So it is using these maneuvers to go there, like this. Okay. It is pointing in the forward direction. Now suppose I make it turn, rotate it like this. Let it go till there and then upright it again. Okay, what about that? So if you look at this, what is being suggested in this figure is that it first changed there was a pure rotation about that point. It went forward and then it corrected itself again and then took small motions. So it may be possible to get into a particular configuration, okay, by following different paths, okay. But the important part here is that the system is fully controllable, so you can go to any point and park. Okay. So simply by looking at this, it would appear that it's very difficult, okay, but strangely, and may not be possible, but strangely, this is a fully controllable system. Okay. Now, more interesting as we come along is, what about this case? I talked about the tractor and the trailer. Okay, this is one car. What if I add a trailer? Okay, so I add a trailer there now. That's my trailer. Okay, now what? Now is it still controllable? That means you can take the tractor and park it wherever you like. Now simply by looking at this is difficult to say. But if you follow this control the algebra, we'll see that this system is also fully controllable. So actually you can go and park wherever you like. Okay. Now let's see further. How do we plan the path for such kind of motions? Okay. Now the car has to follow a sequence of motions to get to wherever we want it to go. So one way of doing it is by using RRT. So rapidly rapidly expanding random trees. This is something we studied a long time ago. So this is the normal RRT, okay, where we have one path. We start off from here. We take a node out. So these are nodes and these are edges. This is something we studied quite a few lectures ago. And we generate another node which is feasible, another node, connect with paths and try and see and connect them. Okay, so if I have a goal point and an initial point, I can connect this tree kind of structure. So I start from one point, get a next node, get another node, get another node, okay, get another node here, okay, and then finally cover the whole workspace and then see if I can connect the initial point to the goal point. Now these are straight lines, these are nodes, these are edges. But in the case of a car, what we see is that we were talking about motions which were like this. So this was my car, and the car actually took a turn like this, then it went straight, then it took a turn and came here. So we are looking at this curvature that the car can take. So we are interested in that turning radius phi. Okay, so the steering angle phi is very, very important for us. So in the case of RRT with non-holonomic RRT, so these are holonomic RRT. In case of non-holonomic RRT, each of these edges are curves, the maximum curve that the car can take. So I can go this side, I can go this side. So this can go this side, this can go this side. Okay, that means this is the maximum steering angle that the car has by which the car can go forward or backward. Okay, so if I go backward, it will be like this. Okay, so please note that these edges are now curves corresponding to phi of the steering angle of the car. So this is a holonomic RRT, this is a non-holonomic RRT. Now let's see how do we proceed further. So we can have bidirectional non-holonomic RRTs, in which case exactly the same way we are starting from the initial point and the goal point in two directions. So we grow two trees and see where they connect. Okay, and so like this is coming from this side, this coming from this side. What we can do is we can, from here we can see which is the nearest node, connect with a straight line and then figure out how to make small nodes and try and connect. Okay, that is connecting or bridging 2 points from two different trees. Now we can also generate a sequence of primitives. For example, this car as shown here. has a turning radius like this, which means that every radius there is possible. Okay, so all these are possible. Okay, similarly in the back side, there's going to be one more which will be like this. So all these are possible. Okay, that means this car can take any path, either in the forward direction or in the backward direction. So if I cover the workspace with this sequence of paths and then connect the initial point and the goal point, okay, to this set of points, then I have a path, because all of this is possible for the car to go. And that is what is basically done by collecting a sequence of paths. Okay. Now, for example, here parking sideways, it goes forward. Then this is my motion 1. This is my motion 2. Okay. So it goes here like this, like this, like this, like this, like this, and then parks there. Now this path may not be optimal. I talked about optimality. That when we talk about optimal here, basically what we mean is that it is optimal in terms of path length. Okay, it should be the shortest length. So in this case, it need not be the shortest length. Okay. Now this is another maneuver. Okay, by which it has gone and parked sideways. Okay, this is the one normally human drivers use, straight and then like this. Okay, but this is also possible. This is also possible. Now, this is not applicable to robots that are not fully controllable. Okay, that means a car that can only move forwards, it cannot do this. Okay. Now, the next question that we come up with is, how do you design an algorithm that is going to give you this? Okay, so we are now talking about designing an algorithm that will automatically generate the sequence of paths and will take a robot from any point to any other point. Let's see how that can be done. Okay, so first of all, how it works is, it is something like RRT only. So we build a tree where each node is a feasible configuration. Okay. So we are going to build a tree from the initial point towards the goal point, where each node is a feasible configuration, and successors of nodes represent configurations where the car can be at del t time later. At each step, consider only one option of setting the steering angle to J minimum or J maximum and backing up and going forward. Now expand the tree as it in an order that minimizes reversals. Look at this. Okay, so here it was here. Okay, we took one curve like this, another curve like that. Okay, then from here I can take one more curve like this and then one curve back like that. Okay, so from here this is one, there can be one more like this. This is one, this and that is another one. So basically build a tree where each node is a feasible configuration. So these nodes are feasible configurations, exactly similar to what we were doing in this case, where we are building here. Okay, so this is exactly what we are doing. We are building nodes which are feasible and then trying to see whether I can connect the initial point to the goal point. It will become more clear in the next example. So let's look at this one. So how are we generating successors? Consider only a set of discrete values for v, which is the velocity, and phi, which is the steering angle. So specifically v is equal to -1 or 1. We say unit velocity. Okay, and phi is equal to minimum or maximum. Either way is okay. Okay, so here if you see, from here I'm generating one node here, another node there. So when it's going backwards, okay, it is going like this. This is one node, this is another node. This is an edge now. Okay, now suppose I generate like this, and from here I generate another one like that, another one like this, and the back side I generate one like this, like that. Okay, similarly from here I generate one that side and one this side. Okay, exactly the same way. So by doing this, I can cover the whole space. I can grow the tree, right? So this is the first one. From here, I have generated one node like this. Okay, so let's have a look at this again. So here, from here, I'm going to generate one node. So it has generated one node here, one node here, one node here, and one node here. Then it catches this node and generates another few nodes. So it has generated another one here. So it caught this one, generated another one, exactly the same way. Okay, and it is catching one node at a time and generating nodes, and you see that it is covering the whole workspace. Okay, so it has covered all the workspace on all possible paths the car can take now. Now you select one path which the car can take, like this, and like this. Then it's a question of selecting a path. There could be more than one path. Okay, So you have to select a path now which is going to take it from the initial point to the goal point. And for selecting the path, we can use A star algorithms. Okay. Now this gave us an example of how we can do path planning for a non-holonomic robot to take it from one point to another point automatically. So the algorithm can actually automatically generate its nodes, and this is an automatic procedure which it can follow. This is the case of the tractor and the trailer problem. So in the previous case, in this case, okay, we were interested only in the case of a car, and the car was having a single non-holonomic constraint that it cannot go sideways. It's a velocity constraint, and we showed that we can have an automatic path planning method similar to RRT. Okay, so RRT for non-holonomic systems, okay, which can generate motions of the car, which is going to take the car from one point to any other point simply by generating these possible nodes and then following it up with edges. So you can see that the whole workspace is being covered. Okay. Now, in the case of a car, it's simple because the theorem clearly states that a robot subjected to a single non-holonomic equality constraint is fully controllable. So we don't worry. But now, what about here? Now let's look at this case. So we have a tractor and a trailer. So this is my tractor. Let's say it's my tractor here. And this fellow is connected by a revolute joint, and there's a trailer at the back now. That's my trailer. Okay, that's a revolute joint then. Okay. So the first question that comes up is, how many degrees of freedom does it have? Now what about this case? If you simply look at it and you are, if you were to figure out whether it is starting from here and is going and parking like that, is it possible? Okay, it's difficult to say actually. Okay, but it's interesting that we'll prove in this case also that this system is fully controllable system, so it can go and park anywhere actually. Okay, provided it fits, of course. Okay, so in this particular case, you see, we have more degrees of freedom. This car itself has, so this kind of car is here having x, y, and theta. Okay, so let's call it theta 1 because it's more than one now. Now this trailer has a revolute joint there, so there is going to be another theta 2 there. Okay, so the car xy and theta 1 is the degrees of freedom of the car in front, or the tractor. The trailer has one theta 2 which is dependent on the angle of the this angle here. That's my theta 2. So in case of this full system, we have x, y, theta 1 and theta 2. So this is a 4 degree of freedom system now. Okay. So the first three are for the tractor, and this fellow is for the trailer, because the angle of the trailer would depend on the theta 1 of the tractor now. Okay, that is because there's a revolute joint here. Now in such systems, we will prove that such a system is also fully controllable. And then the next question would come, how would you plan its path to take it from any point to any other point? Okay, so what we looked at today is essentially the question of controllability. That is, when we are having a system subjected to non-holonomic constraints like this, how do we ensure that, first of all, is the system fully controllable? If it is fully controllable, then how do you build algorithms that will take it from some point to some other point and enable it to park? Okay, and we can do that only by using controllability algebra. So in the other question we look at in the next class, that is this tractor and trailer problem. First, we have to prove that it is fully controllable. Then the question of having an algorithm of how would you move it to some position. Okay, in the case of the car, that was not required because it is already proved that cars subjected to a single non-holonomic constraint is fully controllable. So you don't need to prove it. Whereas in the tractor trailer case, there is a 4 degree of freedom system now. Okay, so that first we have to prove. Then you can have an algorithm which is going to take it from one position to another position. So we'll stop here today. Thank you.